Okay, this is a complex variables practice final exam. I'll go through this at a relatively quick pace. You could scroll ahead and try the whole thing on your own if you want, and then come back and check all the answers, or do it problem by problem. I'm just going to go over these problem by problem, and let's jump right into it. Okay, and this assumes that you're done with a complex variables course, or you've studied it for a while and you just, want to review or practice for a final exam. But here is complex variables practice final exam. So number one, let f of z equal z bar squared over z for z not equal to 0. So express f of z in terms of x and y, where z is x plus iy. So here we go for letter A. Let's go through letter A. So we're going to let z equal x plus iy. Then z bar equals x minus iy. Substituting in, we have right here the f of z equals x minus i y squared over x plus iy. Okay, we expand this, multiply by the complex conjugate, and again, the mathematics in between the computation, integration, whatnot, and algebra, arithmetic, I'm going to go through. I don't show some of it. Some of it I do show, but after expanding and rewriting, we arrive at this conclusion for f of xy is not equal to 0, 0. So this is just expansion, algebra. That's what f of z becomes. X cubed minus 3xy squared over x squared plus y squared plus y cubed minus 3x squared y over x squared plus y squared. Okay, so moving into letter B, determine whether f is continuous at z equals 0 if we define f of 0 equals 0. Okay, well here, we're going to find the limit as z approaches 0 of z bar squared over z. Change this to polar form, so z is re to the I theta, z bar is re to the negative I theta, so z bar squared is r squared e to the negative 2I theta, and then we're going to get here z bar squared over z, r squared e to the negative 2I theta over re I theta, that equals re to the negative 3I theta. Okay, modulus of that, absolute value of that yields r. Now, that yields r. As r approaches 0, r approaching 0, we have a limit as z approaches 0 over this becomes 0. So this, due to this relation with r, changing it to polar, this becomes 0. So it comes out to a number. F is continuous at 0. Okay. Letter C, determine whether f is complex differentiable at z equals 0. So what we would do here, f prime of 0 equals limit as z goes towards 0 of f of z minus f of 0 over z. Remember, f of 0 is 0. F prime of 0, the limit of this is we have that z bar squared over z. That becomes a limit as z approaches 0 of z bar squared over z squared. Change to polar again. Changing this to polar, and we get e to the negative 4I pi. Now we're going to check some values of pi. Let pi equal 0, because this depends on the direction of pi. I'm sorry, I misspoke. Theta. Let's go back. Theta, let theta equal 0. Depends on the direction of theta. Don't know why I said pi. So let theta also equal pi over 4, but first do pi equals 0. Now here, down here, if you take a look, along the real axis, e to the negative 4I, letting this equal 0, you get e to the 0, that equals 1. Okay? However, here, if we let theta equal pi over 4, e to the negative 4 pi I times pi over 4. This is e to the negative pi, which comes out to a negative 1. So these do not match. Since they do not match, we can say the limit does not exist, and it is not complex differentiable at z equals 0. Okay, so that takes care of letter C, A, B, C, and that's number 1. Again, I'm going to go through these fairly quickly because you can always scroll back to see, or scroll ahead if I'm going too slow for you, whichever. You always could pause the video to see if something makes sense or not. Okay. Number 2, find all complex numbers z satisfying e to the z equals negative 1 plus I. Write the answer in the form of a plus bi. So let's do this in steps. Step 1, let z equal x plus iy. Then e to the z equals e to the x plus iy. Use Euler's formula. Okay, that's Euler's formula. E to the x times the product cosine y plus I sine y. We're going to set that equal to the negative 1 plus I, that e to the z. After that, step 2, match the magnitudes. So take the absolute values of e to the z, set it equal to the absolute value of negative 1 plus 2i. E to the z equals e to the x. And then the magnitude of the negative 1 plus 2i is root 5. Okay. Set e to the x equal to root 5. We solve this using, basically solve it using our algebra here. Take natural log on both sides. That eliminates base e. Here we get ln of absolute value, ln of square root of 5. That could be written here, ln of 5 to the 1/2. So x is 1/2 ln 5. Now that we have that, match the arguments. Okay, we could say this component of Euler's cosine of y plus I sine of y has to be equivalent to negative 1 plus 2i over root 5, square root of 5. So our argument in this situation is going to be y equals negative 1 plus 2i plus 2 pi k, k and z. Okay. So that being our argument, step 4, we're going to find the argument. We're negative 1, 2. Think about where that is. That's in quadrant 2. So 45-degree reference angle, right? 135 degrees looks like, well, I'm sorry. Using our reference angle, rather. Okay. Negative 1, 2. Sorry, I was thinking of something else. Let's just go back. Negative 1, 2 is in quadrant 2. Reference angle is inverse tan of 2. My apologies for misspeaking. So the argument, quantity negative 1 plus 2i, is going to be equal to pi minus, right, because it's in quadrant 2, this inverse tan of 2. So that being said, we're going to wind up with y equals pi minus inverse tan of 2 plus 2 pi k, k and z. So when we put all of this together, we're going to get this for our z. Z equals 1/2 ln of 5, right? Okay, what we had here at x, 1/2 ln of 5 plus I, and then we have this quantity here, pi minus inverse tan of 2 plus 2 pi k. Don't forget about the plus 2 pi k, and k is in z. Okay, so that takes care of number 2. All right, moving along to the third one. Okay, for this integral here, okay, we want to use the residue theorem. Denominators, take a look, set them equal to 0. Z is 0, z is I. So automatically both lie inside absolute value of z equals 2. So let's get the residues. Residue here, z equals 0. So residue f of 0. Take the limit as z approaches 0 of z squared plus 1 over z times the quantity z minus 1. You get 1 over negative I, which is going to become I. Okay? Now here, residue at z equals I, f comma I, equals the limit as z approaches I. All right. Let's see what we do here. We just go ahead and use algebra, and we arrive at 0. Okay, so we could apply the residue theorem. Okay, for this integral f of z dz equals, remember, 2 pi I times the sum of the residues. Well, sum of the residues is 0 plus I plus 0. So this would be 2 pi I times 2 pi, 2 pi I times I, 2 pi I squared, 2 pi times -1, and we just arrive at -2 pi for the answer there. Okay, so that takes care of number 3. Again, I'm going through these rather quickly. Okay, 4. Suppose u of xy equals x cubed minus 3xy squared. We want to find the harmonic conjugate for v of xy. So here's what we do first for letter A. We use the Cauchy-Riemann equations, okay, with partial derivatives here. Okay, u partial derivative of x equals v partial derivative of y. U partial derivative of y equals negative v partial derivative of x. So taking the derivatives, this u sub x equals 3x squared minus 3y. U sub y is negative 6xy. So just using what we know, v sub y now is 3x squared minus 3y squared. We take this v sub y, or the partial derivative of y of the v, right? Integrate with respect to y. When we integrate that, we're going to get v equals 3x squared, right? Y minus y cubed plus g of x, right? Now, we use that partial derivative of x with the v, so v sub x. That's going to be just 6xy, taking the derivative of g of x, that's just g prime of x, okay? Now, with the u sub y, partial derivative there, with y, that's going to equal negative v sub x, negative v partial derivative of x, just saying sub x to save time. Negative 6xy equals negative quantity 6xy plus g prime of x. That's what's substituting those values. So what we want to do here, again, we're finding a harmonic conjugate. We just set g prime of x equals to 0. So g of x is going to equal a constant c. So what we could do, we have our v over here, g of x, that's our constant, c. Put these together. Therefore, v of xy equals 3x squared minus y cubed plus c. So that takes care of letter A. Letter B, we want to construct an analytic function f of z equals u plus iv. Okay, right here, here's what we do. X plus iy cube it. Okay, take x plus iy and cube it. We expand, all right? And what's going to happen in this situation, f of z is just going to come out to z cubed plus ic. Take your c value at 0 equals 0, and in the very end, our analytic function could just be f of z equals z cubed. So that takes care of part B. That's 4A, 4B. Let's go right into 5, which is true and false. For number 5, state whether each statement is true or false, briefly justify. So we'll go over this rather quickly. A, every entire bounded function is constant, okay? And by Liouville's theorem, that is absolutely true, as far as we know. For letter B, if f is analytic and the modulus f of z is constant, then f is constant. That is also true by the maximum modulus principle. An analytic function with constant modulus must be constant. Okay, for letter C, every harmonic function is analytic. Well, that's false. Harmonic function is real valued and satisfies Laplace's equation, but need not be complex analytic by itself. So that is false. And letter D, if a function satisfies the Cauchy-Riemann equations at a point, then it is analytic there. That is also false. Cauchy-Riemann equations at one point are not sufficient to justify that statement. Okay, so that takes care of number 5. Number 6, we could get through quickly. Compute the following integral directly using parameterization. We have this gamma z hat dz, z bar dz, where gamma is the upper semicircle, absolute value of z equals 1, from 1 to -1. So if we go ahead and parameterize this, z equals -it, and that would be along the interval from 0 less than or equal to t less than or equal to pi. Then z bar equals e to the negative it, and dz in that situation would be ie to the it dt. Okay, so we have the z bar dz, that's going to equal e to the negative it times the quantity ie to the it dt, and that's going to reduce to I dt. So integrating along this gamma, z bar, that's going to be from 0 to pi. That's our interval, 0 to pi, in terms of single variable t. So I dt, that's just going to come out to I pi. And then that's it. From 0 to pi, integrating that, we get I pi minus 0. So the final answer there is just I pi. Okay, so moving forward to number 7. Okay, number 7 here, find the Lorentz series of f of z equals 1 over z quantity z minus 2. Valid in the annulus, 0 less than absolute value of z, annulus of z less than 2. And also identify the type of singularity at z equals 0. Okay, so what we want to do first, think Calc 2 in this situation. Split this up into partial fractions. So when we split this up into partial fractions, 1 over z, z minus 2, that's equal to a over z plus b over z minus 2. Okay. A is equal to -1/2, b is equal to 1/2. F of z equals -1 over 2z plus 1 over 2 times the quantity of z minus 2. Okay. I skipped a couple steps there, but that's from Calc 2, partial fractions, and you may have seen it in other courses. Step 2, we want to expand the second term. Expanding that second term, the 1 over z minus 2, there, that's going to equal -1 over 2 times 1 over 1 minus z over 2. So for modulus of z less than 2, 1 over 1 minus z over 2, okay, this is what this becomes. That equals, think of the series, n equals 0, going to infinity, z over 2 raised to the n. Okay, so writing this up here, 1 over z minus 2 equals -1/2. Okay, think about where that -1/2 comes from. The summation there, that of from n equals 0 to infinity of z over 2 to the n, right? Now what we do on both sides, we're going to multiply by 1/2. We're going to get this 1 over 2 quantity z minus 2 equals -1/4 times that summation that we have here. Okay, just did some arithmetic there. F of z equals now -1 over 2z minus the summation here, n equals 0 to infinity, z to the n over 2 to the n plus 2. And remember stuff from Calc 2, how to rewrite these with the series. And you probably went over that again in complex variables taking the course. So this becoming this, we could say it's valid for 0 is less than, the modulus of z is less than 2. So the singularity at z equals 0, so the singularity at z equals 0, there is a 1 over z term only. Z equals 0 is a simple pole. So simple pole at z equals 0 is what we could conclude there for that portion. Okay, so that's 7 with the Lorentz series. And let's move on now to number 8. Okay, so we have this integral from 0 to, So, this is all in one. What's it easy? Let me just rearrange this. Sorry. Let's see if it works now. Okay. That's a 2 pi upper bound there for that limit of integration. So evaluate 0 to 2 pi d theta over 5 plus 4 cosine theta using contour integration. Okay. So here's what we do. We use z equals e to the I theta. Take the derivative here. D theta is going to wind up dz d theta, right? So d theta comes out to dz over iz when we perform those operations. In addition to that, cosine of theta equals 1/2 times the quantity z plus 1 over z. So this is what you want to do first, is know what you have here, here, and here. Then this 5 plus 4 cosine theta, that's going to become 5 plus 2 times the quantity z plus 1 over z. And simplifying that as one fraction, you get 2z squared plus 5z plus 2 over z. Okay, so we have our contour we're integrating here. So we have this I equals this. Modulus of z is 1. 1 over this times dz over iz, right? Okay, so substituting, we just substituted there. Now we have I equals 1 over I modulus z equals 1 over this contour, right? Z dz over 2z squared plus 5z squared plus 2. Now, factoring this denominator, this becomes, factoring here, 2z plus 1, that quantity, times z plus 2. So this we write in factored form. So, from here, set these denominators equal to 0. We're going to get z is negative 1/2, z is negative 2. So automatically the poles are at z equals negative 1/2, z is negative 2. However, okay, dealing with a unit circle here, only z equals negative 1/2 lies inside the unit circle, right? So, let's see what we could do here. Residue concentrated at z equals negative 1/2. So we're going to take that residue, that limit as z approaches negative 1/2, right? For z plus 1/2, okay, over 2z plus 1, z plus 2, right? We could reduce this, the 2z plus 1's go, if we factor this out, 1/2 2z plus 1, if we factor that out. And then we wind up with 1 over quantity 2 times z plus 2, evaluating that at z equals negative 1/2. And we're going to wind up with, after the arithmetic, 1/3. And then all we have to do at the end is I equals that 1 over I times 2 pi I times what we have here for that residue, 1/3. And that becomes just 2 pi over 3. So number 8 is 2 pi over 3. Moving along to number 9, we let f of z equals sine of z over z to the 4th. Part A, classify the singularity at z equals 0. Okay, so to do part A, what we're going to do is we're going to use the Taylor series here, sine of z. This is odd, z minus z cubed over 3 factorial plus z to the 5th over 5 factorial plus, I'm sorry, the signs alternate. That would be, so it goes minus, plus, and then it would be minus z to the 7th over 7 factorial, and then on and on and on, that pattern with alternating signs. Now what we do with this, okay, think of this as stuff you did in Calc 2, similar to this in Calc 2, with writing these and also in complex variables. Divide by z to the 4th. We're going to divide that by z to the 4th, so it's going to be sine of z over z to the 4th equals 1 over z cubed minus 1 over z 6z plus z over 120 minus, so they're alternating signs, dot, dot, dot. So in this situation, the Lorentz series has finitely many negative powers for the Lorentz series. Okay? The highest negative power is going to be 1 over z cubed, that first term. So therefore, in this situation, when we're classifying the singularity at z equals 0, therefore z equals 0 is a pole of order 3. Pole of order 3. Okay? And for part B, it's not too bad. Find the residue of f at z equals 0. Okay, the residue is the coefficient of 1 over z from the expansion. Sine over z equals 1 over z cubed minus 1 over 6z plus z over 120 minus thus. So what we could say here, the residue of f0, when you just do your arithmetic there, is just negative 1 over 6. That's all. Negative 1/6, done. Okay? Residue of, so not even c, 1 over z. There's a 1 over z term. Residue is the coefficient of that 1 over z. Negative 1 over 6, negative 1 over 6. Okay, that is what we have there. And number 9, here we go to number 10. Okay, so we have this integral to evaluate. Modulus equals 3. E to the z over z squared, quantity z minus 1 dz. Okay, so again, this situation, we're going to use the residue theorem. Step 1, we identify the singularities. The integrand here, we're going to write as f of z as e to the z over z squared times the quantity z minus 1. So we could see that the poles occur where the denominator is 0. So z equals 0 happens twice, so it's a pole of order 2. We set those equal to 0. Z equals 1 is a simple pole. Happens once. Both lie inside the contour. Modulus equals 3. Or absolute value of z equals 3. So here we go. Integral f of z dz. 2 pi I times the, what we have here, the residue of f comma 0 plus the residue of f comma 1. Okay? That's step 1. Step 2, we get the residue at z equals 1. It's a simple pole residue of f1, limit as z approaches 1 of z minus 1 times e to the z over z squared times the quantity z minus 1. And we just take that limit here. We write this as limit as z. That's a z, sorry about that, approaching 1. E to the z over z squared. E over 1 squared equals e. Okay? So the residue r of f comma 1 equals e. Okay? Now from there, step 3. Residue at z equals 0. Now this is a pole of order 2. So for a second order pole for the residue f comma 0, what we're going to do is we're going to take that limit as z approaches 0, d derivative with respect to z, d dz, over this times of this z squared and f of z. Okay? So when we compute that, right? Compute z squared f of z equals e to the z over z minus 1. Now we're going to differentiate with respect to z. Okay? Differentiate that with respect to z. Use the quotient rule, and you're going to get that e to the z times the quantity z minus 1 minus e to the z over z minus 1 squared. So right there. Now we're going to evaluate at 0, get the residue of f comma 0, and then that just becomes, when you substitute, that becomes negative 2 for the residue. And then at the very end here, applying the residue theorem, we take the sum of the residues. We had an e here, right? And plus a negative 2. And then we're going to take that and multiply it by 2 pi I. And for this, we just wind up with 2 pi I times the quantity e minus 2. So that as the evaluation of that integral, and that takes care of that one. Okay, so moving along to number 11. Okay, suppose f is entire and satisfies. Okay, we have the absolute value of f of z less than or equal to a plus b times z squared, right here, for constants a, b greater than 0. Prove that f must be a polynomial of degree at most 2. Okay, so we have a proof here. This is an interesting one. So step 1, what we're going to do is we're going to use Cauchy estimates since f is entire. That being said, it's analytic everywhere. So for any r greater than 0, we have Cauchy's estimate gives this, right? That f to the nth power of 0, that has to be less than or equal to n factorial over r to the n. And then we have the max, we have the modulus. The max of the modulus set equal to r of modulus of f of z, right? Now, look at what we're given, right? Okay, so we are given a modulus of f of z is less than or equal to a plus b times the quantity of the modulus of z squared. So on the circle, absolute value of z equals r, and then the modulus of f of z has to be less than or equal to a plus capital B r squared. Okay. So what we could say from this is, hence, if we take the modulus here of f to the n over nth power over of 0, okay, that has to be less than or equal to n factorial times the quantity a plus br squared over r to the n. Okay, so that is step 1. Now what we want to do now here for step 2 is we want to analyze for large r. So what we're going to do is we're going to rewrite this modulus of f to the n of 0 less than or equal to n factorial times the quantity a over r to the n plus b over r to the n minus 2. Okay, so we're going to let r approach infinity, and if n is greater than or equal to 3, okay, think about why that would be 3, then a over r to the n approaches 0, and then b over r to the n minus 2 will approach 0. So what we could say here is, therefore, if we take the absolute value, the modulus here of f to the n of 0 equals 0, for all values of n greater than or equal to 3, we could go ahead and say from here, f of n of 0 equals 0 for n is greater than or equal to 3. So we could move along after this step 2. All right, we're almost there for this. We have one more step to go in the procedure. We want to use the Taylor series. Okay, so the Taylor expansion, okay, what we have here about 0 is going to be this f of z. Okay, so it's going to be equal to the f of z is a summation from n equals 0 to infinity. We're going to get f of n of 0 over n factorial times z to the n. So we're going to use this. Now, since all derivatives of order 3 and higher, in this situation, if we write out this f of z, right, a naught plus a sub 1z plus a squared z squared. This is what we have. Since all derivatives of order 3 and higher, they vanish. Okay? Automatically, f is a polynomial of degree at the very most 2. Okay? So that's our answer there. F of z is a polynomial of degree at most 2 at the end. But we needed to go and we needed to show all the steps where we could arrive at that conclusion for that one. So that takes care of number 11. Okay, let's go on to number 12. Okay, number 12, let f. Okay, let f let f be analytic inside and on a simple closed contour C. And suppose the modulus of f of z equals 7 for all E and C. Okay? So, for all x, rather. For all x in C. Okay. Okay, so first question. Can f attain a value with modulus strictly larger than 7 inside C? Justify carefully. So, step 1. Modulus principle. If f is analytic and non-constant in a domain, then the modulus of f of z cannot attain a maximum value in the interior. So the maximum of modulus of f of z must occur on the boundary. Okay, that's step 1. Step 2, we apply the hypothesis. So apply the hypothesis on the boundary contour C. The modulus of f of z equals 7. So we could say, thus the boundary modulus is constantly 7. Therefore, the maximum modulus on the closure of the region is at most 7. If there existed a point inside C where the modulus of f of z is greater than 7, then the modulus would achieve a larger value in the interior than the boundary. And that would happen, that would contradict the modulus principle. So that is step 2. Now from there we could arrive at our conclusion. Okay? So let's go back to the question. Question was, right? Question was, can f attain a value with modulus strictly larger than 7 inside C? So our conclusion in this situation is no. F cannot attain modulus strictly larger than 7 inside C. Okay? So what we have here is the modulus of f of z is less than or equal to 7 throughout the interior, right, of C. And if f is non-constant, then in fact the modulus of f of z is less than 7, strictly inside the contour. So that conclusion, we basically say that is an absolute no. Okay, so that takes care of 12. Okay, moving along, let's see, 13. So 13, let me move these out of the way. So 13. Okay, okay, there we go for 13. Hopefully you could see that. Okay, sorry about that. Old-fashioned setup. Okay, evaluate the integral from negative infinity to infinity of x squared over quantity x squared plus 1 times the quantity x squared plus 9. So, let f of z equal z squared over quantity z squared plus 1 times quantity z squared plus 9. And what we're going to do in this situation is we're going to integrate over the standard semicircular contour in the upper half plane. So in this situation, we find the poles. Poles are at z plus or minus I. Z is plus or minus 3i. So if we're concentrating on the upper half plane, we're going to concentrate on z equals I, z equals 3i, right? Now, from here, let's go ahead and apply the residue theorem. Since the degree of the denominator exceeds the numerator by 2, the integral over the large semicircle vanishes as r approaches infinity. So what we could say here is down here is thus from negative infinity to infinity, f of x dx is going to be equal to the 2 pi I times that residue of fi f comma I plus the residue of f comma 3i. So what we want to do now is we want to compute the residue at z equals I. Okay? So, factor the denominator. We get the quantity z squared plus 1, quantity z squared plus 9. That becomes z minus I times z plus I, z minus 3i, z plus 3i. For the simple pole at z equals I, okay, we get the residue of f comma I. That equals the limit as z approaches I of quantity z minus I times z squared over that product you have in the denominator. Now, just simplifying that, okay, those z minus i's, they cancel. We're going to take this, evaluate at z equals I, perform the arithmetic, we get I over 16, okay? That's for that component of the residue at z equals I. And now we want to compute the residue here of z equals 3i. So doing that, compute the residue, plug in that 3i, perform the arithmetic here, we get negative 3i over 16. So again, we want to add those two residues together, I over 16 plus a negative 3i over 16. We get negative I over 8. And then what we do, remembering I squared is negative 1, simplifying this from negative infinity to infinity, integrating f of x dx, that's going to just be the 2 pi I times the sum of the residues. And that reduces to pi over 4. And that's all for that one. That's all for number 13. So moving along to number 14. Okay, and number 14, we let f of z equal 1 over z squared plus 4. Use the residue theorem again to evaluate here on this contour f of z dz, and then you have the modulus of z minus 2 equal to 3, or absolute value of z minus 2 equals 3. Okay, first step here, find the poles. I'll go through this quickly. Z equals 2i, z equals negative 2i. Then determine which poles, this is important, lie inside the contour. So the contour is absolute value of z minus 2 equals 3. So solving for that, that's think of circle centered at 2 with a radius 3. Okay? Go ahead and check each pole. So at z equals 2i, we find the distance from the center. We get root 8 equals 2 times root 2. Is that less than 3? Yep, 2 root 2 is less than 3. So this 2i, z equals 2i, that pole is inside. And if we do the same thing with the z equals negative 2i, that also conclusion we could arrive at, negative 2i is inside. So again, once we get here, we can compute those residues. So the residue at z equals 2i, okay, perform this. Residue of f comma 2i of limit as z approaches 2i of z minus 2i over z minus 2i, z plus 2i. We could cancel out the z minus 2i's. And this residue of f of 2i is 1 over 4i. Okay? Residue of z equals negative 2i. Well, plug it in, reduce. We get 1 over negative 4i. So this isn't bad at all. Add the residues together, 1/4. Okay, this should be an I. Sorry about that. Right, that should be an I. Adding those residues together, they get 0. Sorry about that. This should be an I, 1 over 4i. Sorry about that. Plus negative 1 over 4i, that equals 0. And here we wind up with 2i times 0. That equals 0. Sorry about the way I wrote that. That didn't really come up as the way... It's not neat. Sorry about that. But you get the picture. It's 0. Okay? So that's 0 there. 15. Okay, so 15. Suppose f is analytic on domain D and satisfies this f of z squared equals z squared plus 1. Show that f cannot be defined as a single-valued analytic function on all of C. All right, so here's what we could say. Step 1, assume such an analytic function exists. Suppose f is the entire and f of z squared equals z squared plus 1. So first thing here after that, factor that z squared plus 1. So it's quantity z minus 1 times the quantity of z plus, quantity of z minus I times the quantity of z plus I. So our zeros here occur at I and negative I. Each of these occur once, so they have each zero has a multiplicity of 1. Now moving along to the second step, what we do is use a theorem about analytic squares. So if g of z equals h of z squared for analytic h, then every zero of g must have even multiplicity. And the reasoning behind that is if h has a zero of order m, then h of z squared has a zero of order 2m. And that happens to be even. Okay, so for this step 3, we have a contradiction. We could say, however, z squared plus 1 has simple zeros and a multiplicity of 1 at z equals plus or minus I. And in this situation, these are odd multiplicities. So this is what we could say. Therefore, z squared plus 1 cannot equal the square of an entire analytic function. There's a contradiction here for number 15. So the conclusion we could say is no single-valued analytic function f exists on all of C with f of z squared equals z squared plus 1. Okay. And now number 16. Okay. Whoops. Number 16, sorry about that. Now I think it's in focus. Yep. Let I of a be the integral from 0 to infinity cosine of ax over x squared plus 1 dx. A is greater than 0. Use complex analysis to show that I of a equals pi over 2 times e to the negative a. Okay, so here's what we're going to do here. For step 1, we consider the complex integral, define f of z, make that equal to e to the I ax over z squared plus 1. Okay? Integrate over the standard upper half plane, the semicircular contour. So think about this. A is greater than 0. So we're going to do here e to the IAZ. That's going to equal to e to the IA times the quantity x plus IY. And rules with exponents, that's going to be e to the I AX minus AY. Okay? Now, what this does, think about what this would do. This would decay exponentially. You got exponential decay, decays exponentially in the upper half plane. Okay? So this is where Jordan's lemma applies, and our integral, and I could say, sorry about that, the arc integral is going to go away. The arc integral in this situation is going to vanish. Now for step 2, we identify the poles z squared plus 1, z minus I, z plus I. So think about this. The only pole in the upper half is going to be z equals I in the upper half of the plane, right? That's where we're concentrating. Now, thinking of that, move along to step 3. We want to now, the residue again. Compute the residue in this form here. Residue f comma I equals the limit as z approaches I of e to the IZ over z plus I. Okay. Now, we could substitute z equals I, and we're going to wind up with e to the AI over 2I. And what's going to happen here is this going to come out to e to the negative a over 2I. And the residue of f comma I, that's going to be that, right? E to the negative a over 2I. That's our residue there. Now we're almost there. Apply the residue theorem in step 4 to negative infinity to infinity of e to the IAX over x squared plus 1. And that's just going to be 2 pi I times that residue e to the negative a over 2I. And that's going to just become pi e to the negative a. Okay, now from there, what do? Okay, we take the real part. Okay, take the real part now. Since e to the IAX equals cosine of ax plus I sine of ax, then we could say this, from negative infinity to positive infinity, the integral thereof, cosine of ax divided by the quantity x squared plus 1, that is equal to that amount, pi e to the negative a, okay, which there, it was, we got that from our residue theorem. Now, think about whether it's even or odd. The integrand, for the integrand is even. Cosine function's even, x squared, even, the quadratic component in the bottom, even over even. The integrand is even, so what we could say is 2I of a, that equals 2. That equals rather, so 2I of a equals pi e to the negative a. Okay? 2I of a equals pi e to the negative a. So, divide by 2. Divide by 2 to get the I of a alone. You get pi over 2 e to the negative a is what we wanted to show. So, there we go. There we have it. We demonstrated that for number 16. And that is all for this exam. I went through it rather quickly for this practice exam. Hopefully this helps you get ready for a complex variables exam. Keep studying. Again, this is just practice or extra practice. All right. Thank you very much and have a great day.